In part 2 of the sorting unit, we'll look at algorithms that try to be a little smarter when they can. And smart means they can exploit if the input is friendly to them to sort faster. And we'll slowly make our way there. So in the end, look at what the current sorting algorithm in Python is using. You may know I had some role to play in this. We'll come to that a bit. But I want to motivate first from first principles what this is about. Adaptive sorting is the idea that you try to exploit order in the input that's already there. Now, the comparison-based lower bound that I showed you in section 3.3, the way I formulated it was for the worst case, but you can actually do the same argument and get a bound for the average case. And if you have this fresh in your head, every algorithm that's comparison-based is essentially a comparison tree. And we argued about that tree needs to have n factorial leaves to distinguish all possible input orderings. And then it needs to have log of n factorial in height. Well, actually, it also has almost all leaves at that height, at least. It can have some leaves higher up, but half of the leaves will be at that depth or something like that. So you can prove that the same bound also holds in the average case. So what this means is, on most inputs, if you have a random input, randomly permuted input, there's no way for you to exploit anything. Because if we have full randomness, that number of comparisons are necessary. And remember, this is asymptotically equivalent to n log n. And so either quicksort or merge sort will essentially do this. But even in the best case, they use this n log n number of comparisons. So usually we can't do much better, but it turns out that what people sort in practice often isn't so random. So you could ask, can we do better if we're, in some sense, almost sorted? And this could happen, for example, if you have data that arrives over time and you occasionally want to sort it. So you have a sorted prefix, then you append new, somewhat random data, and then you sort the entire list again. You could try to do this smarter, but with Python, there's no need to. You can just call sort on the entire list, and it will be as fast as doing some custom-made sort the last part and merge the two or so. Also, if you use sorting to do statistics of some time series, and the time series is, say, a temperature measurement, you won't jump randomly around. It will be somewhat smooth if the time steps are not too big. If you have data that comes from various sources and is roughly ordered, but then you merge those, you might write a specific merge method that does this cleverly, but you might also just concatenate them and call sort. In Python is essentially the same speed. So some of these scenarios could be solved differently, but people started to not do it because it works so well with the sorting method. So the goal for the algorithm would be to adapt to the input. The more it's sorted, the faster it should become. That sounds great, right? But how could you possibly build something like this? How could this work? Let's start with a stupid, simple idea. What if before we sort something, we check, is it already sorted? And if so, we don't sort it. That obviously works in that the best case is now just checking that the thing is sorted. That's the minimum you definitely need to spend. Any sorting algorithm that should be correct has to check that the input is sorted if it is. But of course, this is only one special case, so it sounds like a fairly useless idea. But remember that our key sorting algorithms, both quicksort and merge sort, are essentially recursive. So if we do the same trick in every recursive call, we might pick up things much earlier. And this idea is as simple as it is. It gets you quite a good way towards a good solution. It's good enough to exploit some ways of pre-sortedness. It's the key idea that we'll exploit, but there's a few things that are problematic yet. So we'll still have to refine it. In particular, if you do a linear amount of comparisons at the beginning of every recursive step, you're by and large, if the input is not random, you're basically doubling your cost or worse. And so maybe that point here should be refined to the more sorted the input is, the faster the algorithm should become. But if there's nothing to exploit, the algorithm shouldn't be much slower than what it could have achieved otherwise. You don't want to degrade the performance on the average case just to buy yourself a small advantage in some corner cases. So that's the challenge in this. Now it turns out for merge sort, you don't have to check the entire input is sorted. You can do something much cheaper after the two recursive calls. So remember, that was merge sort. We just find the middle by index arithmetic, sort the left half recursively, sort the right half recursively. And then there's a single comparison that I can do. If everything in the left half happens to be smaller than everything in the right half, I can check with one comparison if the entire input is sorted. And that's super cheap. That's definitely worthwhile doing. Also, if that comparison comes out as not smaller, then you have to do some work. So it seems like this is just as good as checking the entire thing for sorted. OK, let's keep that idea and see how far we get with it. Much of what I'll show you now could be stated more formally as proper theorems to show you exactly what's possible and what not. But I decided to instead keep some indicative examples that show you what happens. Yeah, the numbers are really small, doesn't matter too much. What you should see here is there's runs, which means sorted pieces that are already in order. And to draw it a bit more carefully, so the last numbers are the smallest, and then these are all up here. These are up here, and these are into my text. That's the numbers, OK? So that's my first example input. We have 64 numbers, but they're actually sorted chunks of length 16 each. What would standard merge sort do? Of course, so the change here is that the algorithm doesn't know that these are ordered in that way. If it wants to exploit this, it has to find out. What would standard merge sort do? Standard merge sort would start with the entire list, then recurse on the left half. Oh, and that actually recurses on the left half, recurses on the left half, recurses on the left half, all the way down, until it has two individual elements. And then what it does is it merges those two elements into this little sorted part of two elements. OK? Once it has done this on these other two, it will take those two runs of length 2 and merge them to one run of length 4. And similar for all the other pieces. That's standard merge sort if it doesn't do the sorted check. If you study this carefully, look at the numbers, and remove everything where the two runs are already in order, you get that all of those merges that are grayed out, you don't have to do. Because in each of those cases, let's pick out this example here. There's 53 and 54, so they're already in the right order, so you don't have to touch them. If you pick out one higher up, then again, the left half is already sorted. So the rightmost element here is this 56. And the right half is also already sorted. And 57 is bigger than 56. So again, it's already sorted. We don't have to do anything. All right? What I put down here is the merge cost of these two variants. That's a useful metric that's a little simpler to analyze than comparisons. Because for comparisons, if you remember how merging worked, it depends on which run is exhausted first, how many comparisons you need in detail. And that can be a bit misleading. Also, the algorithm still has to produce this merged output. So you could pretend merge cost is the size of the 2 merges, which is the number of writes that you have to do. And so if standard merge sort in this case needed 380, we now are down to a third of that. So that sounds like it works pretty well, right? Now, of course, this example was chosen so that it works well, and we'll see another example soon. But let's try to analyze this a bit more general. This was just one concrete example. If you look at what happened in the previous example, we had a sorted length, a sorted run of this length. And basically what we saved is sorting that thing. So if we sort with merge sort something of length L, that has effort that costs us L times log L merge cost and comparisons. So that would be exactly the cost of creating this with merge sort if we had to sort it. So in a sense, that's the perfect phase. We saved exactly what we would have had to spend to sort that part if we call merge sort just on that subsegment. And so we could take the overall cost of standard merge sort, ignoring the sortedness, and subtract the best possible thing we could save. And what's the best possible thing? We take the length of all the runs, so L1, L2, L3, and so on. That's the length of these already sorted segments. And we subtract Li log Li for each of the runs. That's the best we can hope for. So we'll call this, I'll call this H because it has some flavor that looks like an entropy, but you can ignore that. It's just a letter to denote it somehow. In a way, that's the best possible we can hope for. So there's no reason why merge sort would ever save more than that. So it's kind of a lower bound for us. And if you look at a different example, so here you have, again, 4 runs and 64 elements in total, but the length of the runs is slightly shorter, 215 and then 2 times 17. Standard merge sort is the same as before. This H value is almost the same as before. Remember, it was 128 when you had the previous slide, all runs of length 16. And what happens if you call our merge sort that does this sortedness check is something like this. It profits at some part, but then there's all these cases where the run boundary overlaps in some sense this part of the input. It can't profit from the sortedness. So we're only realizing half of the savings, which sounds maybe not so great. All right, maybe we need a different idea. Let's try a different variant of merge sort. I'm not sure if people have seen bottom-up merge sort. It's a variant that's a little less known than the standard recursive one. The basic idea is to do, instead of a recursive step, you work yourself from smaller runs to longer runs. Let me explain the code briefly, and then we can look at an example. So at each step, we have a queue of runs that we have to merge. And initially, we say, OK, I don't know anything, so the runs I have to merge are individual elements. And then in the next phase, I always go through my queue, and I take the first 2 elements, which are runs, and I merge those and store that in the queue for the next round. OK? So in the round 1, I would take the first 2 and merge those. And remember this. So I create a new queue. I take 2 elements out of the old queue and merge those. And I put the result into the new queue, the Q prime. Q and Q could be the letter or the word Q. So you'll have to insert the right meaning. So we go through this as long as we have pairs. And then we swap the roles of Q and Q prime if you want. So in round 1, we take pairs and merge them. Now we have runs of length 2. In the next round, we take, again, go through the queue and just take the first 2 and merge them. So we'll have runs of length 4. And then at round 3, we're done if we have 8 elements initially. Okay. Now, why am I telling you this? Is one other way to do merge sort. Why is this useful? If you look at how we initialize the queue, we're going through the list and decide every element you're a run of your own. And there's no reason to do that. We could instead just scan forward and check how long are things increasing. So I move through the array once. I keep track of the endpoint of the next run. And while that is increasing, so while the next element is bigger than the previous, I just increment that and enqueue the run that I find that way. For those reading the code carefully, there's a boundary check missing. You somehow have to check that j doesn't run past n. So you can imagine that there's some sentinel value that stops that from happening, minus infinity, I guess. That's just to keep the code on one slide. Otherwise, it wouldn't have had this nice correspondence. So we only change phase 1. We initialize the queue differently by scanning through the input and finding sorted segments. All the rest is grayed out because it's unchanged. That's pretty smart, right? Now we detected exactly the sorted runs in the input. So that should do much better. Let's see if you followed this rule. So here's suppose we run the standard bottom-up merge sort, not the one that tries to find sorted segments. That's why I gave you letters. Suppose they're not ordered already. So the standard bottom-up merge sort, in which way would it split those 5 elements? It might be better to try to get both on the screen again. Just about. Many people have cast their vote. Some people are still typing or thinking. Right. So let's see. Most of you got this right. Let's briefly go over it. So why is it the first outcome, the first policy? We go through our queue in the same order, and we don't look at how long the runs are. So in this first round, we merge these 2, then these 2. And then there's this last element, which is the lonely run part here. So whenever we have an odd number of runs, we'll just leave the last one lonely and copy it over to the next queue. And so that's what happens here all the time. We merge the first two, and then the third is again lonely. Only in the very last step it gets merged. Policy 2 is standard top-down merge sort. And policy 3 is the same if you round up instead of round down. Right? Good. So if we do our smart bottom-up merge sort, where we detect the runs, this is what happens. This is, again, just repetition from before. That was how top-down merge sort with the sortedness check did. Same picture from before. And as comparison, the bottom-up one. So it immediately finds those runs, so it doesn't even recurse all the way down to individual elements. And it merges those up and achieves cost that is close to h, this lower bound of what we could possibly wish for. And so it looks pretty good. Now, unfortunately, it also has its problems. And the example from the Slido question alludes to that a little bit. Bottom-up merge sort is not at all adaptive. It just merges things as they come along, independent or irrespective of how big they are. And that's not a smart idea. If you have an input like this, then our bottom-up merge sort would treat this very long run that it finds in the input the same as all these short runs. And so over and over and over again, it repeats merges with this long run, and that's just driving up cost. Whereas our top-down merge sort with the check didn't do that, or it wouldn't do that. It does some more interesting things on the right, but then this long run is only merged once. Okay, So it looks like both of the approaches, taking simple variants of merge sort, don't quite always work. They both have their cases where they're fine, but then others where they're not so effective. It would be lovely to have one method that does it all. So at this point, it's useful to maybe pause a bit and ask, what do we actually need? Both of these solutions came from simple hacks or changes to existing merge sort variants. Maybe that's not exactly the right way to go. And conceptually, I think you can split this. There's two tasks. We have to somehow find inputs if we want to use them. We have to detect runs in the input. And that gives us the lengths of these runs. And then in the second step, though, we have to somehow determine in what order we want to merge those. And this was dictated by the code in both of the cases. Bottom up didn't at all look at the run lengths. It just merged them up by pairs. And top down did this somehow automatically from the recursion without much explicit thinking. So let's do the explicit thinking, though. I'll draw this kind of diagram a few times. So you've seen it in the examples before. This is a merge tree. It just means that you take two runs and you produce the merged result of merging the two children. And you can repeatedly do this. So you merge those two input runs and you produce a run here. And then you can merge another input run into this intermediate result and obtain a longer input run. So any kind of possible merging order is a binary tree over the runs. That's what you can observe here. And also the total cost is just summing up the gray area. Why is that? If you have an element like the 20, how often does it play in a merge? Well, we pay for this run when we produce that result. And we pay another time when we have this result. And that's all. So whenever we write an element, we pay for it. Now you can express this cost in a slightly different way. You can also say I'm not looking at these long lines, but instead I'm counting every element, how deep it is. So if number 8 is in a leaf at depth 1, 2, 3, it's merged 3 times. So number 8 should contribute a cost of 3 to the total. So I could also sum the length of all the paths from the root to each of the elements in the leaves. That's the same as the sum of the gray areas. And because the leaves are all at the same depth, you can say it's the number of elements in the leaf times the depth, and you sum this up over all leaves. Why are we doing this? It turns out that this quantity has a name. It's called the external path length of this binary tree. And that connects it to a well-studied problem, the problem of finding the optimal binary search trees. Sometimes people see this as an example for dynamic programming algorithms in some algorithms class. This is a special case of it, but doesn't matter too much. The important bit is there's known algorithms to find the best possible such tree. So you can take any such algorithm and plug it in to do this step 2. That's what I did 5 years ago when I was a postdoc in Waterloo in Canada. So we made that observation of this connection and found some not exactly optimal algorithms, because those are slow. Instead, something that gives you a tree that's almost as good as optimal, nearly optimal. There's several such in the literature. Not all make sense for turning them into a sorting algorithm, but 2 did. And those lead to these 2 algorithms that we'll briefly discuss. And you can prove that they are never far away from this quantity h that I introduced earlier, the best possible case you can hope for. And they're very quick to do, so they don't need a lot of extra time. I want to show you the one that nobody uses first, because that one is easier to explain. And I think it's kind of underappreciated. It's a very nice algorithm. But there you go. It's called peak sort. The reason it's easier is because it's a slight twist on top-down merge sort. Not much changes. But instead of top-down merge sort just cuts the array in the middle and then you recurse, instead peak sort looks at the middle and tries to find run boundaries. So what that means is you treat the whole array as the interval 0 to 1, then you find the mark 1/2, and you start scanning in both directions. Scanning means from this point, you try to find things going down. From this point, you find things going up. So you find the middle run, the one that contains this half mark. So you have 2 possible split points if you want to keep that run where it is. And you do this maybe natural thing. You take the split point that is closer to the 1/2 part. So this one's closer, so we cut here. And that becomes the last merge we'll ever do will be that part and that part. But it's top-down recursive, so you don't see this. You just have that implicit in the recursion. Same as standard merge sort, but you just choose a different point to cut. It's a recursive algorithm, so you do the same in the left and right subtrees. Again, you find from the middle run, you find the 2 boundaries, and the one that's closer to 1/2 is where you cut. Do that on the right side as well. And if you keep going like this, you naturally stop at a run, because say in this left run, in this left recursive call, you jump in the middle and you scan until you find the run boundaries, but then you notice, oh, it's actually my entire input, so I don't need to do anything. And the same happens for all those other leaves. And when you come back, you just merge as in top-down merge sort. You can do it essentially like this. If you want to be a little smart, you want to avoid scanning long runs several times. You spend the comparisons to detect the run, so you don't want to do that over and over again. So by remembering, so a normal recursive call for merge sort would say, you sort recursively from L to R, some range in the array. We additionally have to remember if there are detected runs on either side. We remember how long they are. If you do that, then you can do a clever recursion. I know this looks wild, but it's not actually a complicated code. It's just a few steps of arithmetic. So the whole trickery is just keeping track of this length of left and right runs that you've already seen to not detect them again. So you have a bunch of cases that I tried to simplify into one case by doing the case distinctions inside the computation of the parameters. If you want to understand why this works, you may want to do an example. I just wanted to have code that fits on one slide to convince you this is not so complicated. And conceptually, it's easy, right? All you do is find the middle run and take the closer cut point. Doing that a bit smart is messy. Pardon?
What should be the middle run? Should be the middle of the array, or
the middle run is whatever you find. You start in the middle of the array and you scan left and right. So you always get this one.
what is this z from L to L plus z?
Well, it's another parameter. So the recursion has 4 parameters, a range and 2 numbers, which are lengths of runs on either side that you already know are runs. And they could be 0.
So what about the elements which are in between L plus delta and R plus delta?
So these elements in here, these are just arbitrary. You don't know anything about them. So the recursive call means this is ordered and this is ordered, but in between it can be whatever. You don't know yet.
You have to increase the size of L and decrease the size of R.
Yeah, basically yes. But you do this recursively. So what you do in pictures, you know this. You find another third run in the middle, and you find the closer cut point, and then you recurse. So in that left recursive call, you again have known runs on both sides. In the right recursive call, you only have one on the right side. And then there's different cases. The annoying bit is, it could be that the known run on the left is actually overlapping the middle point. Then you want to not scan that again. So these are a few annoying corner cases. That's why you have these if statements here. Yeah, and initially you call it like this. As I said, this code hasn't really found as much use, so I don't want to spend too much time on it. You're fine if you keep that abstract idea in mind. That's all we need. The code, so this slide is just my proof of concept that it fits on one slide. I wanted to show the same example we had before, where both of the algorithms didn't do so well. So in particular, here's the comparison with the bottom-up merge sort did really poorly on this one because it has one long run and then many short ones. And the standard merge sort with the sortedness check did a bit better, but you see H is quite far away from that still, and peak sort gets very close. So it looks like we can have the best of both worlds. This is one concrete input. You can't really define asymptotics for one input, right?
In most of the cases, because we are dividing it, because we are dividing the whole area.
The complexity of this overall thing is h plus 2n. And whatever h is, h can be between linear and n log n. So I guess it can be between 0 and n log n. And it depends on the input what h is. As I said before, there's no hope if your input is random, h will be roughly n log n, and no possible algorithm can exploit anything if there's nothing to exploit. But if the input has this structure of many long runs, then the algorithm will pick it up.